Does continual gravitational collapse always end in a black hole? The answer is not necessarily. It could be a black hole or a naked singularity or a horizonless compact object or something that we are still to figure out. So before I begin, I should comment on this. Yesterday's there were some unanswered questions about the 14 curvature invariants that we can construct for the Riemann tensor in 4 dimensions. So the list is correct. I2 and I5 are both there. You can refer back to the previous slides and just download them from online. Okay, and there's a reason why the square of r mu nu is also there. It has something to do with algebraic independence, and that for a perfect fluid, once you take the square and come to I5, you have cross terms like pressure and density which are not present earlier on. So both are needed. I've given the reference to the paper in those updated slides. You can download them. And that paper actually says 16 curvature invariants, but later people showed that 2 of them can be derived from the other 14. So 14 are algebraically independent. Then there was a question about why the Kretschmann scalar was not in that list. Kretschmann scalar being RIKLM. It turns out you can write the Kretschmann scalar as linear combination of these 14, using 3 of these 14 things, because you can write the Riemann as Weil plus Ricci. So square of Riemann is Weil square plus Ricci square plus something more coming from the curvature scalar. So that is, and what is a curvature singularity? If any one of these 14 scalar invariants blows up, it's a curvature singularity. One or may blow up, but some can blow up without the others blowing up. Okay. All right. So I was told that the Schwarzschild metric was not derived in the class, no? So I will do that quickly. And then we move on to gravitational collapse. So centrally symmetric gravitational field in vacuum. Vacuum does not mean that there is no matter. It means you are outside a spherically symmetric distribution of matter, like a spherical star, which can be made of anything inside, or that doesn't matter. All that we want is that the matter distribution inside should be spherically symmetric. Then the exterior, where there is no matter, that's called the vacuum. So this is a generalization of Newton's law of gravitation. In the simplest case of, let's say, if we assume the sun to be spherical, matter distribution to be spherical, no rotation, what is the gravitational field outside? Okay, so this is the first example we are solving Einstein equations for, after having written them down yesterday. So these equations are not easy to solve. They are nonlinear partial differential equations, 10 of them. So to start solving, you make some symmetry assumptions on the space-time itself. So in the present case, the space-time is assumed to be spherically symmetric. So you sort of guess what is the natural metric you should write. So since it is spherically symmetric, there would be 2 angles, theta and phi. So the line element there would be d theta square plus sine square theta d phi square multiplied by some arbitrary function k of r and t, where r is your radial coordinate. So this term is natural. Then there would be a term proportional to dt square, again a function of r and t. A term proportional to dr square, again a function of r and t. Here this is h, this is l, and a cross term. This is the most general metric you can write down for a 4-dimensional spherically symmetric space-time, vacuum or otherwise. Now we are allowed to make coordinate transformations up to 4, but theta and phi we don't want to disturb, don't want to mess with the spherical symmetry. But we can make coordinate transformations from r to r prime, from t to, so r as a function of r prime and t prime, t as another function of r prime and t prime, and by doing that we can choose, for example, this a to be 0, this function a to be 0, so that the metric is diagonal, and we choose by convention the function k to be minus r square, so that if you find the area of a sphere with a radial coordinate r, that area would be 4 pi r square. That is clear from this form of the metric. So using these two coordinate freedoms, this first line can be simplified to where e to the nu is just rewriting of L. This is minus r squared, so we brought it to the Lorentzian form, and h dr square is minus e to the lambda dr square. So this is the metric we will work with. Yeah? Yeah, please. Which one is 0? A, is it? Yeah. Why did we take a to be 0? As we saw yesterday, you can make up to 4 coordinate transformations, x, y, z, t, to x prime, y prime, z prime, t prime. So which means out of the 10 metric functions, 4 are free, because you can change them. So I am making 2 coordinate transformations from rt to r prime t prime, so that in the new coordinate system a is 0 and k is minus r. I can always do that. It is not an assumption. So these should be now t prime and r prime, but I have dropped the prime index. Is it clear? Otherwise, please ask. It's okay? All right. More questions? So this is the metric we will work with. Yeah, it has how many free functions? E to the nu is a function of t and r. E to the lambda is a function of t and r. Plug this into the left hand side of Einstein equation. Right hand side is 0. We are in the vacuum, but of course we have at the back of the mind that there is a source somewhere. So soon we will see where the source shows up. These equations are written in vacuum. So what are those equations? There are only three Einstein equations. The rest are like 0 equal to 0. So what are those 3 equations? The simplest says that lambda dot is 0. Okay? Lambda dot is 0. That is, lambda is a function only of space. Okay? Then there is an equation which you can read off from here. Prime is partial derivatives with respect to space. Okay? So put lambda dot equal to 0, that is lambda function only of space. So this is a partial differential equation only with spatial derivatives. This can be solved to show that lambda plus nu is a function only of time. Okay? That basically when you integrate this equation into the integration, you will get an integration constant that will be a function only of time. It can't be just a constant, it will be a function of time because my nu is still a function of time. But I still have one more coordinate not really coordinate freedom. I can go from some t to t prime, t to some function of t prime, because I can then just absorb the rest of the time dependence in this E of nu. Okay? So you can go from t to t prime, you will get something else here that doesn't matter. You call that your nu function. So in other words, lambda plus nu can be said to be 0. Okay? Is that all right? Not so clear. No? So how to explain? This is t, go to some t prime. That changed my nu here. Let it be changed. I have not said anything about nu so far. Choose this function is, choose this nu in such a way that this function is 0. Okay, please think about it. Lambda plus nu can be taken to be equal to 0. So then nu is minus lambda prime. If nu is minus lambda prime, nu is minus lambda, substitute that back here, solve this equation, you will find that exponential minus lambda is equal to exponential nu. This is a 1 plus a constant by r. So I've solved this system now. This system solves to these equations. Now so now I bring in that there is a spherical object sitting somewhere. Very far from that object, the metric should be of the form g naught naught, which is 1 plus 2 phi by c square, the Newtonian form, and the Newtonian potential will arise, phi is negative, if the constant is minus gm. Okay, this is how this constant gets fixed. There should be a r here, equal to 1 minus 2 gm by rc square. Yeah, yes. Sorry about this. No, what am I saying? Yeah, there should be a r here. There should be a r in the denominator. So because I know what form this should be g naught naught, e to the nu should be g naught naught, very far away, g naught naught should be Newtonian, 1 plus 2 phi, and phi is minus gm by r, so this constant should be minus gm. So I've fixed the entire solution, plug all this back in here. This is the Schwarzschild solution, the vacuum solution. Just read it out. ds square equals 1 minus 2 gm by rc square into c square dt square minus r square times the spherical angular line element. Please just check, okay, if there's a question. Okay, good morning. Minus 1 over 1 minus 2 gm by rc square dr square. So please, this is the Schwarzschild. Anything to ask? The t to t prime not very clear, yeah? Please look at Landau-Lifshitz or think about it. All right? I can set this to 0 by making a coordinate transformation from t to some other t. Okay, this is what we need to start talking of gravitational collapse. A spherical body with radius less than 2 gm by c square is in general relativity, it is a black hole. Okay, but just notice at r equals 2 gm by c square, the metric has a coordinate singularity, but if you calculate the Riemann tensor there, it will not diverge. So it's a coordinate singularity, it is not a curvature singularity. R equal to 0 is a curvature singularity. Okay, so we want to now make a transformation to a new set of coordinates in which r equals 2 gm by c, r equals 2 gm by c square is the Schwarzschild radius. Want to make a transformation to new coordinates which don't have a coordinate singularity at the Schwarzschild radius. Okay, and that is a very interesting coordinate system. We'll also then be able to see why the inside of a Schwarzschild radius is inaccessible. Once something is inside the Schwarzschild radius, it is going to go to r equal to 0. We can see that quite easily just by making a good coordinate transformation. So this is the coordinate transformation. I think this was done first by Lemaitre, and then there are others, Eddington, Finkelstein, Kruskal, Zakaris. This is what we do. So
earlier the metric we obtained,
this one.
that is solved by putting e mu equal to 0. That is outside some spherical.
Yes, here, yes.
Now can I use this metric to look into this object? For example, I want to find this Boltzmann scalar at r equal to 0.
Yeah, we are saying it's out. Yeah, there is nothing. There is You can think, at the most think there's a point mass at R, but you have to be careful about that also. Point mass solution is shown to be Schwarzschild, that's a separate story. But yes, I can, what is the problem?
But should be such that this, the radius of this object should be less than 2 gm by c square, otherwise no.
For this solution to be valid?
Inside this object.
No, I'm not, so outside the sun also this solution is valid.
But what about inside?
Inside the sun?
Yeah.
No.
If I want to use this Boltzmann scalar at r equal to 0 and to show that it indeed have a singularity.
Provided there is nothing anywhere. It's a vacuum, so you have like a delta function source at the origin at best.
That will be true if the radius is less than 2 gm by c square.
Radius of the object.
Yes.
I cannot use this inside the sun. I have to use it in vacuum. It's a very idealized solution. I cannot find the curvature at the center of the sun using this.
Because we don't know the energy moment tensor.
Yeah.
When we say the black hole has a singularity at its center at r equal to 0, we calculate the Boltzmann scalar using this very metric.
Yes.
Then this is possible because the radius of this object is less than 2 gm by r square.
The radius, this object has no radius. It's at most a point mass. There's nothing here except at the single origin. There's no object. Yeah, T mu is 0 everywhere, right? That's why the solution is valid inside 2 gm by c square also, except that these coordinates will break down. R and T change role, but I can write new coordinates where the solution is well behaved all the way up to r equal to 0. You'll see that, yeah? Then we can discuss again. It's a long talk, but I don't want to hurry. Maybe I do it in 2 parts, today and tomorrow. We'll see how it goes. All right. So to answer your question and to convince ourselves that this is not a curvature singularity, we make a transformation from t little r coordinates to tau capital R. What is that transformation? Ignore the plus minus, take plus for now. Tau is equal to Ct plus this function f we will just now specify. Capital R equal to Ct plus this. Yeah? It's a well-defined coordinate transformation. Because earlier I was using little t here, and little t and little r. Now I transform to tau and capital R. Okay? Choose the function f, this is a choice we make, to be root 2m by r, or maybe there's a gm by c square. Understand that when I write m by r it is dimensionless, and whenever I say m by r I mean gm by c square. Okay? Choose this function, do the integration. Okay, the integral is quite straightforward to do. Start here. This is root 2m by r. So just substitute this here. You can do this integral. You will get capital R as a function of t and little r. Similarly, do this integral. You will get tau as a function of t and little r. Invert. Then you can write little r as a function of capital R and tau, where Rg is the Schwarzschild radius, 2 gm by c square. So you can have a look, you can stare at it, but it is very straightforward. Yeah? I have made a coordinate transformation. I have prescribed how it is to be done. In the new coordinate system, this is what my metric looks like. ds square equal to c square d tau square. So notice earlier there was a 1 minus 2m by r term here that has gone away. The coefficient g naught naught is 1, c square is 1, g naught naught is 1. There are no diagonal terms. g0 alpha is 0 where alpha is spatial. Such a metric where g naught naught is 1 and g0 alpha is 0 is called a synchronous coordinate system or a synchronous metric, okay, because essentially you have synced all the locations. Minus d capital R square over this fellow minus this coefficient Rg to the 2/3 times the spherical line element. So my Schwarzschild metric after that coordinate transformation has become this. Is it okay? Now look at R equals 2m. R equals 2m, namely R, that's defined as Rg. So little r, if it is Rg, you substitute here little r equals Rg, then r minus c tau to the 2/3 is Rg to the 1/3. So this is the constant. At r equals Rg, little r equals Rg is the Schwarzschild radius. At little r equals Rg, this is finite. It is just something into Rg. So you have now seen that the Schwarzschild radius coordinate singularity has gone away in these new coordinate systems. Whereas if you put little r equal to 0, r minus c tau is 0, and if r minus c tau is 0, this will blow up. So there is still a coordinate singularity at the Schwarzschild origin. That is also a curvature singularity. The Riemann tensor blows up. Are you okay with this now? Questions? Yeah, and this is important. Timelines are geodesics. What does that mean? If I am staying put at one place, my capital R, my theta and phi coordinates, capital R, theta, phi are not changing. I am staying put. So d capital R is 0, d theta is 0, d phi is there, ds is d tau. This is a timeline. Timeline meaning my position is not changing, just time is changing. Very interestingly, timelines in this coordinate system are geodesics, meaning in these coordinate systems, if I am at a particular value of capital R, I'll stay there. You can't do that in a Schwarzschild capital R. You leave some ball there, it will fall into the star. But in these coordinate systems, they are very curious coordinate systems. In this coordinate system, in the geometry of a spherical object, if you leave some object, the integrand has a pole at r. Is the integral well defined at r equals 2m? Yes, it is. The integrand has a pole at r equals to 2m. No, there is no pole. Okay. In terms of capital R equals, little r equals 2m, capital R is just r, some power of r. R minus ct, just theta, just some power of rg. So it's completely well behaved at the Schwarzschild radius. So what I am saying, timelines are geodesics. You understand that? In an inertial coordinate system, if I am staying put x and t, if I stay at any particular x, my t is changing, that's a geodesic. In the same sense, capital R equals constant is a geodesic. I'll stay put there. And that's a very useful coordinate system. A given little r corresponds to capital R minus theta equals constant. If you choose a little r, particular little r value, you will get a line r. This is got a straight line in the tau capital R diagram. So now what do I do? This picture is from Landau-Lifshitz, Classical Theory of Fields. I plotted the capital tau R plane, suppress theta and phi. In this plane, I show lines of constant little r. Remember, little r is the Schwarzschild coordinate. Those lines are straight lines. This is a line little r equal to 0. This is the line little r equals Rg, the Schwarzschild radius. This dashed line is outside the Schwarzschild radius. This dashed line is inside the Schwarzschild radius. You get that? Little r equals, so in the Schwarzschild coordinate system, if you are staying put at some point, at that staying put at some little r, your capital R and T are changing in such a way that that is a little r equals constant is a straight line. So I've drawn those straight lines. Any questions here? Now, what are the radial light rays? We want to prove that from inside the Schwarzschild radius nothing can escape, it will go to the center. What are my radial light rays? Put theta and phi as constant. I get d tau by dr as d tau by dr is just this function, which you can easily show is root rg by r, because r is given by this relation. It's very straightforward. This is it. D tau by d capital R is plus minus root rg by r, plus for outgoing geodesics, minus for infalling geodesics. Now let's see what is this line telling us. I have drawn the light cone at a point A outside the Schwarzschild radius and a point A prime inside the Schwarzschild radius. Schwarzschild radius is Rg. If I am outside, R is greater than Rg. This look at infalling geodesics for now. In magnitude, d tau by dr, the slope of the light rays will be less than 1 if I am outside. So that is explained here. The slope is less than 1. You can see that these dashed lines are the light cone. The slope of the light cone null curves is less than 1. The line little r equals constant is a 45 degree line, because you can see here little r equals constant is having a 45 degree slope. That line is inside the light cone. So that motion is causal. I can be at some little r and move, if I fall in from there, that motion is causal, or I can be at a little r equals constant. It is allowed. Does that make sense? I mean, you start free falling from there, of course, but little r equal to constant, you are allowed to stay there if you want by applying some force. That is not allowed now inside r equals rg, because when r is less than rg, the slope of the light cone is greater than 1. So the line little r equals constant at a point A prime inside the Schwarzschild radius, that line lies outside the light cone. No matter what force I apply, you cannot stay there, because that motion is not causal, it's not allowed by special relativity. So where will you go? You have to go inside, because you might think you can come outside. How do I just? So it's an infalling geodesic, no? You say infalling geodesic by definition is not coming out. I'll come to the outgoing geodesics also in a moment. Infalling geodesics are such that little r equals constant is not allowed inside the Schwarzschild radius. This slope goes to, as r goes to 0, this slope goes to infinity. This will cut r equal to 0 at vertical angles. So since you are not allowed to stay there, you have no choice but to proceed to the singularity. So in that sense, it is a black hole. Okay? Nothing is allowed to stay there. Have I said everything clearly or not? Please ask questions.
So why r is equal to constant not allowed
Inside, because it is outside the light cone. Any physical trajectories have to have slow speed less than speed of light, so they should lie inside the light cone. This fellow is not inside the light cone, so it's not a physical trajectory. Its r must change. Okay, so it is in that sense that you can't be at rest inside the Schwarzschild radius, you have to proceed to the singularity. So once inside the Schwarzschild radius, you have no choice. You have to proceed to the center. There is so that's what essentially what we mean by a black hole when we say that nothing can come out. Okay? There is an opposite solution called a white hole. Let me not get into that. That is for the positive sign here. You can have a singularity from which everything is coming out. Let's not go into that. That's a time reversed solution. Okay, so this is all I need for the Schwarzschild geometry, and these things can be proved. I will not do it to just now. This can be proved just from what I've told you and looking at the geodesics. Seen from far, a collapsing star takes an infinite time to reach RG. This you know, no? A body from outside of a stone is falling towards in a Schwarzschild geometry, and you ask how much time little t passes, how much little t time passes, that is infinite. For a far away observer, it takes if I'm very far, I'm seeing something fall towards r equals rg, it will take forever. However, in the freely falling frame, it takes only a finite time to reach rg. So this is the novelty of time dilations in general relativity. If you are falling towards a black hole, namely a region which is less than any region which is any mass m, which is localized so that its radius is less than rg, is a black hole. If I am freely falling in the gravitational field of a black hole, I will cross the Schwarzschild radius in a finite time. Seen from a far away observer, it will take an infinite time. But I will not even know that I have entered RG. There's nothing written there, right? Schwarzschild radius here, do not cross. So you go in and then you'll get stretched. The tidal force will just stretch us. The Weyl tensor will be on work. It will stretch us and whatever. But of course I should say that we'll talk more about it. This is what general relativity is saying, that there's a singularity there, but singularities are not physical. We don't know really what is happening there. Maybe quantum gravity effects are removing the singularity. Maybe you are going to another universe. We really don't know. GR says there's a singularity, but in reality what is going on? And in fact, I will talk more about this. From the viewpoint of the faraway observer, a black hole never forms, because the star is shrinking. It takes forever to reach the Schwarzschild radius. And an object of size less than Rg does not exist. This is very important. For a faraway observer, the black holes that we are seeing in the sky are for all practical purposes black holes. It's becoming infinitely closer to the Schwarzschild radius. The velocity approaches speed of light as the Schwarzschild radius is approached. As the star approaches Rg, the emitted light gets infinitely redshift. For all practical purposes, a black hole. So something different is happening for the freely falling observer compared to what is happening for us seeing it from far. Now, there is another possibility that is allowed, which if there is time, we will go to in the end. Who told us that the freely falling observer will necessarily go in? If you have a star, maybe it will go close to the Schwarzschild radius, but some pressures, exotic equation of state, it will stop sometime before Rg. That's what we call a horizonless compact object. HCO for short. Horizonless compact objects have become very popular So that's when a star collapses, does it form a black hole in the sense of the freely falling observer? Even that we don't know. There might be very strong pressures, and so I'll also tell you what are the singularity theorems, because you will say the singularity theorems of Hawking and Penrose say that singularities do arise. What those theorems say is if some surface called a trapped surface forms, then a singularity will form. What is the trapped surface? A region from which light cannot escape. Outgoing geodesics as well as ingoing geodesics will just go in. That's a trapped surface. So R equals Rg is a trapped surface. Once you are inside, you will proceed to a center and singularity will form. But who said that we will enter? Maybe you have a star, you are an observer sitting on the surface. So in other words, for those of you who study neutron stars and white dwarfs and pulsars, we are told a star heavier, what's the limit? 2.4? 2.4? Yeah. A star with a mass, collapsing core with a mass greater than 2.4 solar masses will proceed to form a black hole. That's what we are told, no? But that's not strictly a correct statement. We don't know, because there may be some other developments take place in the matter inside, and it just goes to the just short of the reaching the Schwarzschild radius, it stops. That's called a horizonless compact object, or HCO. Because of gravitational wave observations, HCOs have become very interesting these days. Maybe a HCO signature in gravitational waves and in shadows, etc., is so-called gravitational wave echoes. The HCO signature could be different from what it would be there, like if a merger of two neutron stars is to form a black hole, give out gravitational wave, or if merger of two stars is to form a HCO, the nature of gravitational waves could be little different, and people are very seriously interested in that. Another thing is, once it enters the Schwarzschild radius, it is going to form a singularity. But the following can also happen. You are a freely falling observer going in. Before you cross Rg, a singularity forms at the center. Nothing says that the boundary has to enter the Schwarzschild radius before the center becomes singular. You see what I'm saying? It's an extended object. Something is happening at the center, the boundary is not yet arrived, the center forms a singularity. Such a singularity can be naked, in the sense light starting from it can escape the star before the boundary of the star has entered the Schwarzschild radius. This is a naked singularity. So we have at least three different scenarios. A black hole forms, a naked singularity forms, or a horizonless compact object forms, and at least one more situation, say in quantum gravity, that the singularity never forms. The thing goes in and whoosh, you go out into some other universe. Such things can happen. Right. The curvature singularity at the center implies breakdown of general relativity, possibly an artifact of the thermodynamic description. We are describing matter as a fluid, perfect or imperfect fluid. We don't know how its equation of state is changing at high densities. And then just observation, black holes are similar to elementary particles. For a particle whose mass is greater than Planck mass, the Schwarzschild radius is larger than the Compton wavelength. That's like a black hole. If the mass is less than Planck length, the Compton wavelength is greater than Schwarzschild radius, like a particle. There's a particle black hole duality just by changing the mass. You make the mass larger than Planck mass, it's like a black hole. You make mass less than Planck mass, it's like an elementary particle. So, yeah, roughly that. You can ask me anything. We change the topic now. Yes. A star is collapsing. its boundary has not yet entered the Schwarzschild radius. The density inside is going up. Think of it as made up of shells, onion shells, all of which are moving in. So the density everywhere is going up, including at the center. The density at the center can become infinite, and hence there will be a curvature singularity before the boundary of the star has entered its Schwarzschild radius. Yeah? Then a light ray starting at the singularity, just before the singularity forms, take the limit, somebody at the center is shining a torch outside. That light can escape. Take the limit that the singularity forms, that light will still escape. That's a naked singularity. Singularity and horizon are two different things. A singularity covered by a horizon is a black hole. Then the Penrose coined this term, they're dressing up the singularity. If the singularity is not wearing the horizon, called it absurd, I don't know, but this is a name Roger Penrose gave. We have to accept. A black hole, the name black hole was coined by John Wheeler. The name naked singularity was coined by Roger Penrose. It's not wearing anything. You can see it as if it's not to be seen, as if it's to be hidden. So that's also sociological, painting the naked singularity in a I don't want to see it kind of way. But I have no problem with naked singularities are a gateway to quantum gravity, because quantum gravity probably avoids the singularity, but you will get to see what's happening there. If it is behind the horizon, you don't know what's happening. I would like to see the naked singularity to know what are the quantum gravity signatures there. So in order to be able to talk about black holes, Roger Penrose proposed the cosmic censorship hypothesis, namely gravitational collapse always ends in a black hole and not in naked singularities. But this is a hypothesis, it's not a theorem, right? You see what I'm saying? And we used to be told there's a difference between a hypothesis and a conjecture. We call something a conjecture when it's likely to be true, like in mathematics, such as Fermat's last theorem was a conjecture. In mathematical language, you call it a conjecture if it is likely to be true. So it's not cosmic censorship conjecture. It's cosmic censorship hypothesis. An assumption I make so that I can do. If I don't know that black holes form, then what's the point in talking of black holes? So you make an assumption that collapse ends in black holes so that you can talk about it. But it's an unproved hypothesis, and there are at least examples in the literature where gravitational collapse is shown to form a naked singularity. Maybe I'll do 2 talks today and tomorrow. I show that in an worked out example of collapse in general relativity, when the collapse ends in a black hole and when it ends in a naked singularity, depending on the density distribution. Depending on the distribution of matter, distribution of density, I can show that one or the other. That's interesting, no? You see what I'm saying? Yeah? Does that answer?
So it's like even if you go inside, you can come out.
Yes.
Maybe you can pass through.
Yeah. If the horizon has not, what is horizon? The boundary entering the Schwarzschild radius, that's the event horizon. If it has not formed when the singularity has formed, you can still come out. That is, a singularity and horizon are two different things. Yeah? Question? So we want to now proceed to answer the thing that we were just discussing, that I will work with the spherical object, a star, which will be made of dust, because I can solve Einstein. Dust is, you did perfect fluids, no, in the energy momentum tensor, yeah? If the pressure is 0, the perfect fluid is called dust. Because there's no, pressure is non-gravitational. It opposes free fall. If there's no pressure, you will fall freely. So if you have a ball of particles which I call dust, they will all fall freely and they may form a singularity. Singularity will definitely form because free fall means there is nothing to prevent you. I throw a stone, it will go to the center of the earth. Why does it stop on the surface? Because there is pressure, there is electron degeneracy pressure. Pauli's exclusion, not degeneracy, it is Pauli's exclusion principle which is preventing. But if there was no pressure, the stone will just go to the center of the earth. Yeah? So you have a freely falling dust ball, it will become singular, but the singularity may be a black hole or it could be naked. We want to see that today. Yeah? Okay, so those solutions of spherically symmetric dust collapse, that solution is known as the Tolman-Bondi or Lemaitre-Tolman-Bondi solution. The dust, it has no pressure, but it has density. It has a density profile, right? The density can change from place to place. In other words, it is inhomogeneous. The inhomogeneous solution is called the Lemaitre-Tolman-Bondi solution. The homogeneous limit is usually called the Oppenheimer-Snyder solution, 1938. But there is a less known Indian gentleman, B. Dutt, who actually published the same solution 1 year before Oppenheimer and Snyder, so which should be called the Dutt-Oppenheimer-Snyder solution. And this is the first example, first demonstration of a formation of a black hole. The Oppenheimer-Snyder solution is a homogeneous dust sphere. The density is uniform. That's the Oppenheimer-Snyder solution. That forms a black hole. But if the density is inhomogeneous, if it is very inhomogeneous, it will form a naked singularity. The closer it gets to homogeneity, those solutions are black holes. This is the phase transition from the naked singularity phase to the black hole. So this is not an HCO. Obviously, if there is only dust and no pressure, you can't form an HCO. To form an HCO, you need a non-trivial pressure, non-trivial equation of state. So, okay, let's proceed. So, I want to do the simplest thing because it's very instructive. Consider in Newtonian gravity the radial free fall of a stone. I drop a stone in the gravitational field of the earth. If it's too close to the surface, then your acceleration due to gravity is a constant, 980 centimeters per second. The s is half gt square. That's not the problem you want to solve. Drop it from a great height so that the acceleration due to gravity will change, right, with height. It is gm by r square, minus gm by r square, where r is the distance from the center of the earth. You understand what I'm saying. So how will I solve that problem? The stone has a mass little m, the earth has a mass capital M, and this is the energy conservation equation, half mv square, r is the distance from the center of the earth, minus gmm by r equals E. So instead of solving the Newton's law of motion, I can solve the energy conservation equation. Write it like this, dr by d tau square. Take the potential energy term on the right hand side. I have written it as capital F by R. What will capital F be? 2 gm, just 2 gm. Yeah, capital F is 2 gm. So in the remainder of the talk, I use these two notations interchangeably. Whenever I write the function capital F, it is 2 gm. Maybe there will be a c square somewhere. Here there is no c square. And what is this function little f? So r dot square is f over capital R plus little f. Little f is e by 2e by m. Yeah, this is clear, no? Now I can integrate this. What do I do? Capital F and little f are constants. So I can bring the right hand side down here and write this as a tau, integrate d tau. This is the solution that I get, which is actually quite straightforward to integrate in the case when the function f is 0. The total energy is 0. I can start from some initial velocity inwards, because if capital E is 0, I have an initial velocity which is gmm by r0, where r0 is where I started from. The solution for little f equal to 0 is very straightforward. Capital R to the 3 by 2 of tau is the starting point, r0 to the 3 by 2 minus 3 by 2 square root of f times tau. At tau equal to 0, I am at capital R equals r0, my starting point. When I reach capital R equal to 0, I just put capital R equal to 0 and I solve for tau. I call that my singularity. I'm hit capital R equal to 0, so you'll see why I call it a singularity. Capital R equal to 0 is tau singular. This, are you okay with this? Yeah? Try to memorize it, we'll need all this. Yeah? This is the amount of time that a stone falling to the center of the earth takes to reach the origin. How will this go? Okay, so this, right. Tau s is the time taken for the stone to reach the center, to reach the earth, which I have assumed to be a point, where capital F is 2 gm. If the total energy is 0, then this is the amount of time taken to reach the center. This is trivial, but we need it now. Right. Gravitational collapse of a dust sphere in Newtonian gravity. Instead of a stone, I have a ball of stones. Each point is a freely falling stone. That is the meaning of dust. Yeah? Nobody is obstructing anybody's motion. Now, let the total mass of the dust ball of stones or particles be capital M of R0, where R0 is the boundary of the ball. Capital M of R is the mass up to some radius r. Yeah? What equation should I solve now to find the trajectory of a specific stone? Clearly, the motion of a stone will only depend on the mass that is inside. That is Gauss's theorem. So what will I write? A stone with a mass little m. One more thing. Shells are labeled by co-moving coordinates. What's a co-moving coordinate? If my co-moving coordinate is little r and I fall, my co-moving coordinate will not change. It will always be little r. Yeah? That's your little r co-moving, moves with you, like my name. Wherever I go, my name is TP Singh. My name is my co-moving coordinate. So same way, little r is the you ignore theta phi. You can put that also if you want. So what is the equation of motion to be found by? Write the energy conservation equation for a stone starting at a location little r. It will always keep that value of little r. What will be the half m? Capital R is changing. Capital R is the distance from the center. That is changing, yeah? Capital R is a function of little r and tau. This is the kinetic energy. This is the potential energy. And this is equal to my total energy. So clearly the solution will be the same as before, but I have put a label little r to distinguish between the different stones. So now write it like this, same as before, except capital F and little f have become functions of the co-moving coordinate. So capital F is this function, little f is this function, okay? And I do the same thing as before. Now my integral over space is over capital R, not over little r. Little r is a constant. So I can still do these integrals because the little r dependence of the functions capital F and small f is immaterial. It does not affect this integration. Again, work with the simplest case, little f equal to 0. what is the trajectory of the little r stone? It's the same solution as before. Trivial, right? Capital R to the 3 by 2 of r tau is little r to the 3 by 2 minus this function. Now, if I put capital R equal to 0, I get what I call a singularity curve. What is the time at which different shells go to the center or become singular? If a shell now shrinks to size 0, its density has become infinite. So I can call it a singularity. Yeah? So this is my singularity curve. Tau s of r is equal to 2 little r to the 3 by 2 over 3 square root f of r. For example, look at the situation. F of r is what? Mass distribution. Mass distribution relates to density like this. Integrate density over volume, you get the mass. So if density at the center, I Taylor expand, so the first term will be rho naught. So it will be rho naught r cube. Right? It's going as r cube. Rho naught, the mass near the center obviously will increase as r cube. So the mass will increase as r cube. There is rho naught here. R to the 3 by 2, r to the 3 by 2 will cancel. You will get 2 by 3 root, and there will be a g, Newton's constant, 2 by 3 root g rho naught. That number you are familiar with. 1 by root g rho has dimensions of time. Are you okay with this? Different shells become singular at different times, and understandably, if the density is decreasing outwards, later shells will become singular outer shells become singular at later times. There can be shell crossing also. If the density is increasing outwards, the outer shells will overtake the inner shells. That's called a shell crossing singularity. We are not interested in that. We will let the density fall out as you go out from the center. And what's the case if the sphere is homogeneous? If the density is uniform, then the mass, a little r dependence will drop out, and the density and mass are just related by mass is density into 4 pi by 3 r cube, right? If the mass is, the density is uniform, then this, otherwise differentiate. dm by dr is 4 pi r square rho kind of thing. You get the picture, right? Okay, why are we doing all this? This is the same solution in general relativity. That's why we did this. Now we go to the next slide. Write down Einstein equations for a collapsing ball of dust, for a dust sphere. The solution is the same. That's why we did this. It's only true if there's dust. If there's pressure, the Newtonian and the GR solutions will be different. Okay, gravitational collapse of a dust sphere in general relativity, the so-called Lemaitre Tolman-Bondi solution. Because it is dust, there is no pressure. The energy momentum tensor has only one component, T naught naught. The density, the energy density, I denote it by the symbol epsilon. Mass density is usually denoted rho c square, because of E equals mc square, rho c square is epsilon, energy density. All other components of T mu are 0. The metric in co-moving coordinates r theta phi is also synchronous. I am not proving this. We will work with co-moving coordinates. For dust, only for dust, co-moving coordinates are also synchronous. Namely, g naught naught is 0, g naught alpha is also 0. And the metric can be written like this. Have a look at this. ds square is d tau square minus e to the lambda dr square minus capital R square. So what is capital R measuring? So the same dust shell, this is the same dust shell. I'm doing this with GR now. Capital R measures the distance from the center of a shell with a co-moving coordinate little r. Yeah? Any questions here? So how many free functions I have? Capital R and lambda. Again write down the Einstein equation. This time there are 4. Last time there were 3. So you can, don't look at the implies right now, that I will explain. Just look at the, so this is the first Einstein equation to solve. I can integrate, I can do the time integration. What did I do? To check, have I made a mistake? Not a mistake, is hiding. You see there? There's a prime there. It's looking like r square, but it's r prime square. That's why I got worried. What happened to the prime? You integrate this over time. E to the lambda is r prime square over 1 plus f of r. There's an integration constant where the integration constant will be a function of space, and choose this initial condition, capital R equals little r initially. I can change my little r to match with capital R initially, and the scaling hence is capital R as a function of little r at the beginning tau equal to 0 is just little r. Yeah. So I solve the last of these equations, substitute for lambda in the first equation. Now you can again do the time integral to get, remember you saw this. This is the energy conservation equation. R dot square equals F over R plus little f is the same equation. That's the beauty of it. The energy conservation equation in Newtonian mechanics follows from the Einstein equations. Basically this is just vanishing of the divergence of T mu nu will do this. Okay. So I have done this. Turns out that you will get nothing new from here. This solution for r dot and e to the lambda you put in here, you will get, so here the right hand side is energy density. There is only one Einstein equation out of the 10 where the right hand side is non-zero. That is this equation. The left hand side will simplify to just give you that the energy density is f prime over r square r prime. Remember what was f? F was like mass. Yeah. So if I do an integration, ignore the prime dependence for now, then this do the integration on the left hand side. F is just in E r square dr. F is like mass. Yeah, that's what we here also. F was nothing but the mass. The same interpretation holds here. The function capital F is like mass. The function little f is like the total energy. So please do stop me. I want you to feel comfortable. We're just solving. Okay? Are you okay? We're just solving Einstein equations. Everybody okay? So we have solved. We can now solve this. Yeah. I know how to integrate this. Once I solve for capital R as a function of tau, I can put that here. My functions capital F and little f have to be prescribed, they have to be given. They are functions only of space. If I give the density profile, initially, epsilon is a function of time and space. Epsilon is a function of t and r. But if I give the initial density profile and put capital R equals little r initially, I will solve for the function capital F, which is a function only of little r. Capital F is a function only of little r. I will get the mass profile given the density profile. So mass profile is m of r. That mass profile does not change with time. That is dust, you know. The same mass profile will hold at all times. Energy density will change because that you compress it, put the same mass in a lesser space, energy density will change, but how much mass is inside a shell, that will not change because that is dust. There is no shell crossing, nobody overtakes anyone else. So the mass inside a shell does not change with time. So that is why this function capital F of r and little f of r have to be prescribed as initial conditions. which is the same thing as saying you have to tell what was my initial density and what were my initial velocities, right? You do to solve this problem like this, you just give the initial position and initial velocity. Initial position is the density profile, initial velocity will determine this function f. Yeah, from here, you give that mass profile, you give the density profile, mass profile will get fixed. Once that is fixed and you tell what's the initial velocity, I will know this function little f. Yeah? And we will work with little f equal to 0. That's called the marginally bound case. If little f is positive, it's bound. If little f is negative, it's like energy, it's unbound. A little f equal to 0 is the marginally bound. Again, please stop me. I think today we'll do only Oppenheimer-Snyder, the homogeneous case. The naked singularity case we'll do tomorrow. Questions, please ask me something. Are you comfortable? Okay. So now I know how to solve this. We just did it in the Newtonian case. Okay, so we can now in a formal way understand black hole formation. How? So this solution, let me write, this is the solution, right? You remember from the Newtonian case that solution, the equation is the same. This is the same equation in general relativity for the collapse of a sphere. I work with little f equal to 0. This is the solution. Remember the solution. What is happening physically? The radius of a shell is decreasing. There will come a time when the radius will go to 0. That will tell me when it becomes singular. That's singularity curve. But before that, something else happens. The mass inside is constant. So what is the Schwarzschild radius corresponding to a mass m of r? It is 2g m of r by c square. To begin with, it is outside the Schwarzschild radius, yeah? Better be, otherwise there's no problem to solve. To begin with, it is outside the Schwarzschild radius. When it reaches the Schwarzschild radius, we say it has become trapped. Because once inside, you cannot come out. Provided the singularity has not formed, we will come to that. Once inside, you must proceed to the center. So different shells enter their corresponding Schwarzschild radii at different times. Are you following that? So what is trapping? If you have entered your Schwarzschild radius, you are trapped. Different shells enter their Schwarzschild radius at different times. They get trapped at different times. So just as we have a singularity curve, we have a trapping curve. Okay, what is the trapping curve? The shell with co-moving coordinate little r is said to become trapped when its area radius, when its physical area radius capital R has become equal to 2gm of r by c square. So tau trapping is the time at which we get trapped. This is the trajectory, this is the solution for the trajectory. In that, put for tau as tau trapping, and this is capital R to the 3 by 2. That will be this right hand side to the 3 by 2, and this function f is nothing but 2m. G goes for a right. F is 2m. That follows from here also. If you put capital R equals little r as in the initial conditions, r prime is 1, capital R is little r initially, and f prime is epsilon r square integral. Do the integral over little r, you just get the mass. Right? Are you okay with this? This function capital F is nothing but 2 times the mass. Please ask me, I want you to be clear. Is it okay? Farus, any question? Capital F, like in the Newtonian case, is 2 times the mass, and mass does not depend on time. The mass inside a shell remains a constant. Okay, to find when a shell becomes trapped, I just put its area radius, the physical distance from the center. So remember, capital R is the physical distance from the center. You can see from here, it's measuring the area of a radius of a sphere. Little r is just a coordinate. It's a co-moving coordinate I'm carrying with me, but my distance from the center is decreasing, and that is measured by capital R. Okay? When my distance from the center becomes equal to my Schwarzschild radius, I have become trapped. So I can put the distance from the center equal to my Schwarzschild radius and work out my trapping time. This is the time at which the shell with coordinate radius r becomes trapped. I just solved this equation, wrote the trapping time tau of t as a function of little r. So there are two curves. There is the singularity curve, the same as in the Newtonian case. This is the form of the singularity curve, and this is the form of the trapping curve. This is just a definition. I'll show you a diagram just now. The boundary of a trapped region is called the apparent horizon. This is different from the event horizon. The event horizon is the last ray to escape the collapsing star. Star is collapsing. The last ray that can leave is the event horizon. Whereas something else, so for if you find, okay, let's see. Look at this trapping function. This is the singularity curve. Remember from the form of the singularity curve, 2r to the 3 by 2 over 3 root f, that's the singularity curve. So this is the singularity time. Obviously there is a minus term here. One gets trapped before becoming singular. A shell is going to become trapped and then becomes, obviously trapping happens when you cross r equals 2m. Singularity requires r equal to 0. So you get trapped before you become singular, except the center. What happens at the center? Let's say at the center f is 0, a mass function, this is 0. For this, as you approach the center, the trapping time approaches the singularity time. The center becomes trapped at the same time it becomes singular. Other shells become trapped before becoming singular. And who gets trapped first? That let's see. Let's look at the homogeneous case. Homogeneous case, density is uniform. If density is uniform, it doesn't depend on little r, it's a constant. Mass will just increase as r cube. Are you okay with this? Constant density, mass will increase as r cube. That is this function. This is a mass function proportional to, this is basically proportional to rho naught. In the homogeneous case, that's the Oppenheimer-Snyder solution, the Dutt-Oppenheimer-Snyder solution. If you probably seen that film Oppenheimer, so at some stage when Oppenheimer is just starting his career due to the beginning of the World War, they mention this paper. Oppenheimer and his student Snyder have discovered a very interesting solution showing endless gravitational collapse. So that this is endless gravitational collapse. In the homogeneous case, the trapping time, if you put f as r cube, this will be r to the 3 by 2, this will drop out. The trapping time is given by this. The higher the value of your r, the farther you are from the center, your trapping time is lesser. Boundary of the star is the first shell to get trapped in the homogeneous case. So once the boundary is trapped, the other fellows also cannot come out, right? Because so this is the formation of a black hole. In the homogeneous collapse, will always end in the formation of a black hole for dust. There can be other situations where inner regions get trapped before the boundary. That depends on the density profile. We'll see that tomorrow. In here, the boundary gets trapped first. Now notice something very curious here. Suppose you had R very large, you would be trapped before you started, right? You started at tau equal to 0, but if you take little r to be very large, you would have, so it means you cannot have a homogeneous dust sphere of arbitrary radius. The reason is very simple. What is the trapping condition? To be untrapped, 2gm by rc square should be less than 1. Sun has 2gm by rc square much less than 1. A black hole has 2gm by rc square equals 1. That is the meaning of saying reaching the Schwarzschild radius. Ordinary stars have 2gm by rc square much less than 1. In the homogeneous star case, m is growing as r cube. So m over r is growing as r square. You take a very large r, you will cross unity. You don't want to do that. So in this particular case, you cannot have infinitely large stars to begin with. So boundary of the star is the first shell to get trapped, and this is a nice diagram. It's good to spend a few minutes looking at it. It shows the formation of a black hole, the DU, the Dutt-Oppenheimer-Snyder solution, 1938-39. The formation of a black hole in gravitational collapse. So time is along the vertical direction, space is along the horizontal direction. The event horizon starts forming at O. We'll come to that, come to the event. And covers the singularity. The boundary of the trapped region inside the star is the apparent. So what is happening? The boundary of the star gets trapped first. Okay? So all the dotted regions are trapped regions. So as first in time the boundary gets trapped, then inner shells get trapped, etc., etc., until everything gets trapped. The center is the last shell to get trapped, and what time does it get trapped at? 2 by 3 root f naught. So okay, here the center has become trapped, and the center becomes trapped at the same time at which it becomes singular. Remember, what is the singularity curve? This is my singularity curve. A homogeneous case, capital F is going as r cube. This is a constant. All shells become singular at the same time. You see that? In the homogeneous case, the singularity time is independent of a little r. All shells become trapped at singular, all shells become singular at the same time. Okay, this is the time at which all shells become singular. Okay, and if you draw inner shell, it will become, it will go like this. All of them become singular at the same time, but they get trapped at different times. The boundary gets trapped first, and inner shells get trapped later. This is the singularity. So your singularity curve is not extending inside. Why? Because they all got singular at the same time. Once singular, always future's gone. This is the trapped region. The last ray to leave the horizon is the event. The last ray to leave the star is the event horizon. And after that, if you start something, if you start a light beam from here, it is going to, it's already trapped. It has reached the boundary after the boundary has become trapped. So it can't escape. If you had started here, you could have escaped. Okay, so read it again. The formation of a black hole in gravitational collapse. The event horizon forming at O, starts forming at O. The event horizon starts forming at some time, and it covers the singularity. The boundary of the trapped region inside the star is the apparent horizon. So the space-time diagram for a naked singularity is going to look very different. So I'll show that next time. But we have nicely covered the Oppenheimer-Snyder solution demonstrating the formation of a black. So now you see the singularity is completely covered by the horizon. It's inside the trapped region. Nothing can start from here and escape. It's impossible. But suppose my singularity had started here, below O. Then light can go out until the point O. Yeah? Once you hit O, you cannot escape. But suppose my outer shell became singular before getting trapped. Is that possible? No, it's not. So for other than r equal to 0, all shells other than the center will become trapped before becoming singular. The center will can sort of saying become singular after being trapped. Something like that is what is happening. If the center is singular but not trapped, things can escape from this. We'll see that next time. Okay, I would strongly recommend you to look at this paper by Professor Jayan Narlikar. The reference is here. Maybe I can even click on it. Yeah, this is a good thing about Keynote. I don't know if I'll be able to go back. I'll try. Right. So this paper by Professor Narlikar, 100 years of GR, 2015, we brought out a special issue of Current Science, when Javian described the growth of general relativity in India before independence. So there's another paper by Professor Dadich, GR in India after independence. So that covers Rai Chaudhary. I don't know which side is Professor Vaidya, before or after, maybe just before. I forgot. So this is where there's a mention of B. Dutt. So there was a school of GR developed in Kolkata by N.R. Sen. I think Rai Chaudhary and others came from that school. And so this is the Sen school, N.R. Sen. Then there was a school in Banaras. So I want to read this about. It's very interesting. Good that we found it. Who was B. Dutt? I sometimes write use D-U-T-T, D-A-T-T is the correct spelling. While reading the Landau-Lifshitz textbook, can you read this? Is it readable? Huh? Readable? While reading the Landau-Lifshitz textbook of classical theory of fields, is Javian writing, I came across a reference to the paper by one B. Dutt. As a postdoc working on gravitational collapse, I found Dutt's approach quite general. In fact, as I discovered the Landau-Lifshitz text followed the method used by Dutt, this work of Dutt was published in 1938. A year later, Oppenheimer and Snyder wrote a paper with similar material content so far as the technique of handling the GR equations goes. The Oppenheimer-Snyder paper is generally regarded as the pioneering work on spherical massive objects contracting with increasing inward speed. This is the solution we did today. We did the Oppenheimer-Snyder paper. Dutt, however, kept his approach general, thus giving solutions not only of contraction but other motions too. More importantly, he had seen the significance of co-moving coordinates in solving such problems. At this stage, one may very well ask what later work by Dutt is found in the GR literature. The answer prima facie is nil. Indeed, my inquiries with relativists from Kolkata belonging to Dutt's generation drew a blank. It was more recently reported by Shaumak Rai Chaudhary, Shaumak was here, that Dutt belonged to the famous Presidency College and was a favorite student of N.R. Sen. As to why no later work by him is reported, the answer is tragic. Around 1940, he died in the course of a surgery that went wrong.